Hello and welcome to Beamerfolk.
Yes, I managed to squeeze two more channels out of this LED and key board. It's probably worth you visiting the first version video that I produced, and that should be linked here, and possibly the second video, which is linked again here. The first video I produced, just to sort of do a summary of this, just in case you haven't encountered this before. The first version I did, I produced the basic 6 scanning digital voltmeters. The second version, the second video I produced, added manual select using the push buttons below, these ones here. And now I have developed this further thanks to the Arduino Nano's ability to have 8 inputs. Their A to D MUX is capable of having 8 inputs. Not all Arduinos have 8 inputs, but the Nano has, and that's what I've exploited. Briefly, for those that don't know, what you've got here is effectively 2 digital voltmeters being displayed simultaneously, and those 2 inputs could be A0, A1 of the Arduino, and as there are 2 inputs being displayed, you've effectively got above 2 LEDs that represent these 2 displays. So as the 2 LEDs scan from left to right, those particular inputs are presented and displayed on this display here. As a digital voltmeter goes, this is perhaps a little basic. Each display can only really display up to 5 volts, so you could get 3.05 say on one, and on the other you could get 1.02 of a volt there. So it's fairly limited, but it can be, with resistive inputs and possibly op-amps, scaled up to any voltage you like, providing protection is applied. Let's now look at the switch bank below. It's very simple. At the moment, the pair is at the top right. If I choose to push the second pair here, you can see that the second pair flash lighting up and the second pair is presented. If I choose to now present the fourth pair, you can see that that reading comes up there. And let's say if I want to look at the third pair, you get the reading presented there, and so on. Before going on to show you the latest script, I thought I'd just show the basic setup of this. You've got obviously the LED and keyboard here. They are still available, but I know that an awful lot of you have got these stashed away. To the left we have the power bank. I've covered the very bright blue LED display on that, and I've got here my filter network, which was the subject of another video, and I'll put a link to that over here. You've got also here a resistive network. There are 9 1K resistors in series attached to the supply of the power bank, and of course the Arduino Nano. The supply voltage of this is critical. So when you program this, of course you're plugging in the USB connector to your PC or laptop or tablet, whatever, and its accuracy is dependent on that supply voltage. Well, those supply voltages can vary and have a lot of noise on them. So the best option is to have this operate via an ancillary supply. In this case, I've used a power bank, but you can use a regulated supply. But it is critical. And what I've added to this is a scaling function within the script, and I'll show that in a minute. That allows you to put a digital voltmeter on a voltage source and compare that with the voltage as indicated here. And actually, I was surprised how accurately you can adjust this. It is actually quite good. I was a little suspicious of the ADC within the Arduino Nano, but there's no need. Actually, it's quite good. I would say you could get this quite easily within 10%, but possibly within 5% accuracy. But it does need a good supply, and that's why I've included that scaling factor. In fact, I needed very slightly less gain in the Arduino Nano, in the overall circuit, to achieve accuracy against my digital voltmeter.
And now to the juicy bit, the script. I've made a few alterations on this, and those items that I've altered or added, I've put in a remark 4 asterisk, similar to that there. So whenever you see those 4 asterisks, you know that I've either modified or added code to this script. To begin with, I tidied up these 3 statements here. I had constant int. It didn't need an int, it actually just needed a byte. There are 0 to 255 possible numbers you can put into a byte, and as these numbers here are all single digit numbers, I thought it warranted changing those to a constant byte instead of a constant int. My OCD frame of mind, I'm afraid. Moving down to the first asterisk, which is here, I've added a variable, again a byte variable, byte size, and you can see the 4 asterisks, and this is the scaling function. This enables this script to be adjusted to a digital voltmeter, so you can compare the digital readings on the scanning digital voltmeter with a reference digital voltmeter, and that's what I did. 100 here represents a scale of 1. As you've noticed, I've got 94 inserted in there, so that I've elected to make the circuit have a very slight negative gain, and that matched my digital voltmeter, and my digital voltmeter is reasonably accurate. Of course, you could use a reference voltage there, but I didn't think it warranted it. Moving on down, we bump into, here we are, we're now gone into the loop. So there we are. Right, within the loop there is a button select, and the buttons, to identify the buttons, it's not exactly 1, 2, 3 and 4. You know that I've added a 4th button to operate the additional pair of digital voltmeters. Well, you would kind of logically think that's button, it's called button 4, but it's not. It's actually called button 8. So what I've done here is assigned in my script 4 to 8. So that's an addition. And previously you can see how this logically moves. 1 equals 1, 2 equals 2, 3 equals 4. So it effectively goes 1, 2, 4, and then my latest edition is 8. The system now knows that whenever it sees a button called 8 pushed, it means button 4. Okay, we've moved down to the start of that's an addition here. What I've basically done here is replicated the buttons 1, 2 and 4, and this is the if statement, that if button 8 is pushed, or button value 8 is pushed, go to switch 4 subroutine. And as you can see, these were previously installed, and all I've done is duplicated this statement and adapted it to, instead of switch 3, switch 4. So that goes to a subroutine. We'll have a look at that in a minute. Well, moving on down, well, let's see where the next 4 asterisks are. We're entering the state machine now with that switch statement and case 10. That's the beginning of the state machine. And it looks as though we're moving into effectively moving the dots across the top of the board. And I think that's all as it was previously. And here we are, we've got another 4 asterisks here. Okay, so at the end of the state machine, what happened here at case 20, we reached a point where, I made a little statement here, we reached a point where at this sequencer it was originally at 10. So effectively the state machine, when reaching at this point here, would return back to the beginning, which is case 10 here. So all I effectively did was duplicate this, changed it to the new LEDs, the far right pair of LEDs at the top, and moving the sequence here, changing it from 10 to case 30, so it would jump to this point here. And when it rattled its way through this code here, it eventually got again to sequence 10 and went back to the beginning. So this is the part that I've added in the state machine. It does other stuff. It's actually quite complicated in its way, addressing subroutines and things. But that was a new addition as well. So that's effectively the end of the loop. And I think we're going to, let's just see. Yeah, see, that's the end of the loop. So we're now going into subroutines. And you can see that I effectively, when I take an analog reading, I take 4 of them and then average that out to a single reading. And you've got 4 asterisks here. Well, of course, this is where the scaling function comes in. Originally, I had dec times 100. Well, I changed 100 to ref scale, and that becomes my scaling factor. So originally on the previous script, that had 100 in there. For my particular setup, it's now 94, I think. So that's the reason why the 4 asterisks are there, because I've obviously changed that. Moving through to more subroutines, let's see where else I've altered. You can get more information on this script as to how it functions on my previous videos, and the links to those I'll put in the description below. So we're now going to, do you remember that when you push a button it goes to switch 1, 2, 3 and 4? Well, this is the subroutines that it calls. And I think when we get to switch 4, here we go. Yeah, so that's the latest edition there. And all I've effectively done is duplicate switch 3, changing it to switch 4, and then changing the addresses instead of C9, CD, instead of CB, CF. And that does the LEDs at the top. Scanning pair function. And is there anything else? Show pair 2. Oh yeah, this is the showing of the digital voltmeter pairs subroutine. And I think, here we go. And this little subroutine here is a duplication of this code here, and all I've done is altered the addresses here. We call it I called it here show fourth pair, whereas the previous one was show third pair, and I've changed the addresses here. What I haven't done is on the remarks, I haven't actually changed the remark statement here. It should actually, in fact, while I'm here, I'll do that. Let's go C, D, and let's go C, F, and then save that, Control S, and there we are. So that's an update. That was an error, wasn't it, on my part? Not to change that. And that's it. That's the end of the alterations. Well, here we are, arrived at the test rig I've built for the 8-way scanning digital voltmeter. And as you can see, it's basically a series resistive network of 9 1K resistors. You have here the connector going to the LED&KEY board. That's self-explanatory. The critical bit here is the supply voltage. It's got here 5 volts DC, and these values are calculated on that exactly. The way I power my scanning DVM is through a power bank, and that supply voltage is in fact 4.66 volts DC. Well, that would have the effect, of course, of dropping all these values. But my PC actually runs at just over 5 volts. So you can see what the slight problem is here, is that if you calibrate the 8 scanning digital voltmeter using the scaling variable called ref scale that I've included, if you calibrate it using your PC or laptop or tablet, then when you plug into the voltage source that you're normally going to use the digital voltmeter on, which for me is the power bank, it's actually got a different supply voltage. So what I had to do was do my reference calibration based on my power bank to get a grip as to whether the voltage, whether the gain of the nano needed to be increased or reduced, and made a slight adjustment, programming it, plugging it into the PC, and then unplugging it and going back into the power bank. Not the most ideal way of doing this, but it was the way in which I generated a reference, a calibration against my own workbench digital voltmeter. And it worked for me, but it is a bit clumsy. And that's about it. There is a supply capacitor here of 100 microfarad I put across the supply, particularly when you're plugged into the PC. It's noisy, and it helps in stability. I hope you've enjoyed this. I hope you find it useful and find applications which I haven't thought of. And if you find applications for this, I'd be very pleased to read your comment to see how you've employed this or how you've put this to work. Oh, by the way, just a footnote. It's worth considering the input impedance of the Arduino nano. Whilst it has a very high impedance and doesn't affect and load this resistor network, it does have a small capacitance built in, and I think it's around 14 puff, which unfortunately means that the driving impedance has to be relatively low. You notice that I've used 1K resistors. Well, the input impedance can't really go much higher than about, I think it's 20k, 10k or 20k. But for being on the safe side, I would probably make it around 4k. So if you were to develop some form of resistive network on here to measure, say, 50 volts as opposed to 5 volts, then that network would probably represent, would need to be looking at an input impedance of 4k, and by the time you put the dropper resistor on there and a couple of diodes protecting them, please bear in mind that this is a voltmeter, doesn't go negative, so protection has to be applied there. The overall circuit would be probably nothing less than well, I'd say nothing less, but nothing more than about 47k, at the most 100k, which for a modern digital voltmeter, that's a bit low, and probably you'd be wise to buffer this by using, say, a CMOS op amp on each input, and then of course the impedance will rise, the input impedance will rise to a high level. This is Beamer signing out for now.